the topic now is the gradient descent. By now, you must be wondering, am I going to do the entire fundamentals 8 sessions on just gradient descent? We never seem to be making progress beyond it, it seems. Isn't it? Anyone wondering that? So, see, the equation for gradient descent was W, weight, right? And I will just use the notation in this book, guys, just for the time being. In this book, weights, it's a weight vector, right? They write it as a theta vector. It's just a convention, right? We write it as, because I want you to review from this book, W next is W minus alpha gradient of the loss with respect to W. This is how we write this equation, guys. By now it's familiar to you, right? Well, gradient is implied to be with respect to W, but if you want to be really clear, you can stick in a little this, right? Any one particular W, let's say W ij of the nth layer, this next value, actually, we typically say, I put next or I just put tilde here. You must be familiar with my tilde symbol here. Tilde is equal to Wij, the current value of the layer, any particular weight. This is the address of a particular weight parameter minus is this. So this is writing it out into the component forms. This makes sense, guys? This is just recapping what we have been talking about all this time, the gradient descent equation. Right. This particular thing is from the ith of the ith node in the lth layer, coming from the jth, the edge connecting from the L-1 layer. The weight on this edge is Wij, right? Wij, right? This is what it is. The actual location of this edge. Where is it? It is the edge between the jth node in the L-1 layer to ith node in the lth layer. That is what we call Wij. Right? This is a review of what we have done. So far, so good. Now, this is, of course, the next value of the parameter vector. What in the world is this? Does anybody recall what this alpha is? Anyone?
Loss coefficient.
The learning rate.
Learning rate.
Learning rate. It's like how big a step learning rate, the intuition is, you know that you have to go that way, but how big a step are you willing to take in that? Because taking a step in the right direction is learning, isn't it? Decreasing the loss, changing the parameters in such a way that the overall loss decreases is learning. But given the gradient, this is what? This is the gradient, right? This is the actual gradient of the loss, gradient of loss. This is the learning rate. Given a certain gradient of loss, this is the gradient of loss is 5, right? How big a step how much you change the value of the parameter, it still depends upon how big a step you're willing to take. That's why the learning rate is important. Now, if you remember, how do you know what is a good learning rate? Do you think big learning rates are good? In general, shouldn't we be in a hurry to learn? Just take giant learning steps, quickly go to the minima? What do you think, guys? What's the counter argument to that?
We
A lot
be
oscillations.
instability.
Yeah, you will hop across in your hurry. You will just hop across the minima, and then you'll just keep bouncing around it, right? So in other words, with big learning rates, you will, sorry, let me do it in a more realistic way. Suppose your loss surface is like this, very basic. Loss surface is like this, and your learning rate is very high. You will go from here to here to here to here. Do you notice what you're doing? You're just bouncing around, right? So you're not getting to the minima. You just are bouncing around here and there. And from this, right, you're again shooting up, going this. So it's just a bounce around. You don't know. You're not converging at all. But what happens if the learning rate is very slow? What's the problem? So now you know.
You reach it very late, right? You go very slow, or you may get stuck in the local minima.
Right. See, what happens is that good minimas sometimes are in a basin, in flat basins. Like if you think in terms of the loss surface, we saw those beautiful visualizations, but I will use this bowl from my hometown. You see this bowl. What does it have at the bottom? Do you see there's a flat basin here? The surface has a flat valley. Isn't it, guys? The valley is nice and flat. It's like Yosemite Valley. Right? What is the gradient in the Yosemite Valley? If your loss surface is the Yosemite National Park, what is the gradient in the Yosemite Valley? If you have been to Yosemite? 0, isn't it? It's flat. Do you agree? It's a nice basin there, right? So when your gradient itself is very small, almost 0, not quite 0, but almost 0, then look at this term. Let me use a different color. Look at this. If this itself is very small, and you take a small learning rate, a small number times a small number, fractional number times a fractional number is what? A vanishingly small fractional number, isn't it? Let's say that your gradient is now already 10 to the minus 5. And your alpha rate is also 10 to the minus 5. So the step that you take, the step size is what? 10 to the minus 10. Yeah. 1/10 trillionth. Isn't it? That is one.
But then in that case, isn't a close enough answer good enough? As in, should we even take a step further?
Yes, but now I'll tell you something bad. Suppose you are in this situation and you are here and you're taking tiny steps and you take 10 epochs and you're out of epochs. Now what? You realize that you didn't quite reach good minima. You get to a plateau,
Right.
well,
Yeah.
you're stuck, right? So, well, what do? Small learning rates are bad, big learning rates are bad. Is there any learning rate that's good? How do we find that?
You talked about momentum.
Yes, I did. I talked about momentum, and that is the topic of today. Today, we are going to learn about 2 techniques that tells you. So when you look at a situation like this, and if you imagine that you have rolled marble, by the way, are you all familiar with what marble is? Maybe I'm too old a generation. We used to play with marbles, throw marbles at marbles. There's a round. Are marbles still around? Not quite. Huh? Okay. Do you guys know what marbles are? There's actually, do I have a box? I used to have one. Okay. Do we know what marbles are? Glass beads.
Yes.
Round glass spheres, right? And children used to play in my generation. So suppose you have a marble and you let it come down the path. If you just leave it on a surface, what will it do? It will roll down the path of steepest descent, isn't it? But as it rolls down, what will it do? It will acquire momentum.
Yes.
Will it stop here or will it stop here? No. What will it do? It will just shoot past happily, go up here, bounce back, lose energy, come back, bounce a couple of times, and then finally settle here. Yeah. So now what was the difference between the marble and the way we are doing in our gradient descent equation? That rolling ball and us and the approach that we are taking, what are we doing wrong? Why are we getting stuck? But our familiar little marble, should it be rolling in this imaginary lost landscape, in this hypothetical surface, lost surface, it would go to the minima just fine. What does the marble have that our equation doesn't have? It is the momentum. Even though the gradient has vanished, it has the momentum of past motion, isn't it? It has velocity.
Yep.
And when we people talk of momentum in this space, right? You assume momentum is mass times velocity, but if you have unit mass, then momentum is velocity, isn't it? Momentum. So we will use that momentum and velocity. We will use synonymously because there's a convention here. And we say that the marble had velocity, it had momentum. So it went past, it didn't stop. But our gradient descent is not smart enough. So one thing that can help us is momentum. We need, so the lesson we learned from this is we need momentum, right?
Yes.
And this momentum is important because the lost surface could be like this. Oh, sorry. This is also possible. So a little bit of a momentum. See what happens is at this point, which way is the gradient pointing? Gradient is pointing, gradient is saying that the direction where the answer is this, isn't it? It is telling you at this point, go here. But what is this momentum so far telling you? It is on a roll. It is trying to go which direction? It is trying to go this direction. Right? If the marble has been rolling, the momentum is in this direction. And so if you consider the effect of momentum and gradient together, momentum, what will happen is the net effect will, the momentum will still win, and it will take you out of a minima, local minima, and tide you over and let you continue your journey. Now you say, well, that is well and good, but what happens here? Because here also it will have momentum. Momentum will take it up, right? Gradient will try to bring it down. Gradient will bring it here. Momentum will take it up, but that is okay. It will just swing back and forth and finally stop here. Does that make sense, guys? So we realize that momentum is a good thing. But there is something else we can do. What we can do is when we are learning, suppose we are running 50 epochs in a vast lost landscape, you randomly initialize the weights, the parameters. You know that you have picked some very odd point on the lost landscape. By the way, should I bring up that visualization again, guys, as a recollection? Would it help? Let's do
This is good so far.
this is it's worth knowing. Guys, this is the heart of this neural network theory. We need to get this right. Make sure if you don't understand, stop me, ask again, discuss with each other, discuss with the
Asif,
yes.
just one quick thing. I doubt if I would follow, if I don't ask this question. The only thing is there was a delay between, your audio and the video, and the two arrow marks that you draw just now. Could you repeat that, Asif? The two arrow marks, the momentum and the gradient.
Yes, and absent-minded is nothing. Okay. See what happens is if you have a marble, right, rolling downhill, it has momentum. At this point, which way is this momentum taking it? It's taking it towards this direction, right? Up direction. And which way is the gradient? The gradient is taking it which direction? The minus gradient is taking it which direction?
Downwards, yes.
Downward, right? So what you do is, if you have sufficiently high momentum, it will sort of cancel out it will slow it down. This gradient will slow the momentum, but it won't completely eliminate it. The momentum will still win, right?
Got it.
And so the marble will keep rolling.
Thanks, Asif.
That's a basic intuition. Do you see how this physical intuition comes in here, right? Actually, if you get the intuition, the rest is just algebraic equations. And in fact, not terribly important. We'll write it carefully and we'll get it right, but it's not terribly important. So the first thing we learn is that we need momentum, isn't it? Let's see that. I'll bring up the visualization and we'll play that game all over again, just to recollect. Look at this. How many of you took the time to play with this beautiful lost landscape? Isn't it amazing? Do you look at this log? Just to recapitulate, guys, look at the sheer beauty of this. It is obviously a very high dimensional lost landscape that has been projected down to 3D. So remember that it is not 3D, it's a very high dimensional that through mathematical magic somehow been projected down to 3D. Where is the minima? The pink is the minima, isn't it? The blue is the deep blues are the highs. Let us actually do gradient descent. Right. So let's start descending from here. What happens? What happened here?
Stuck. Minima.
You got stuck. Let's try from here. Again, you got stuck. Repeatedly, we are getting stuck, right? Now, let's see what happened, why it got stuck. Do you notice that if you look very carefully, there is a valley here. Do you see the plateau here?
Mm-hmm.
There's a plateau or a tiny little valley, little bump, pothole kind of a thing. And unfortunately, our not so smart descent got stuck here. So what are the things that we can do? One is we can take bigger steps. So, you know, a little ant can get stuck in a pothole, but you would imagine that if you come with a big truck with big wheels, it's unlikely to get stuck in a pothole, right? It's making big steps, right? Or imagine that you have a dino walking the streets or an elephant walking the streets. It wouldn't even notice a pothole. The trouble is it's making big steps moving forward. So let's try and play with that and see what happens. What we are going to do is we are going to give it some, first of all, let's descent rate, scaling, panning, wheel rotation. Let's do one thing. Let's give it some momentum. Let's give that marble a chance. And what we are going to do is we are going to start at exactly the same place. Where did we start? Did we start somewhere here in the beginning? Maybe I'll start right here, just so that you know this is it. What happens? Do you notice that it went further? This time around, it went a little bit further, but unfortunately, it still got stuck. Maybe some more momentum. Let's try that. Is that what's going to do?
So, Asif, when you set that momentum, it's going to be constant throughout the journey, right?
Yeah, for now.
Okay.
But we will actually revise that. It's a hold that thought in your mind.
Yeah.
Today's lecture is all about. It's very fascinating, actually.
Yeah.
I find it very, very fascinating. So let's try to come down this path again, and I'll do exactly the same point and see how much it helped. For me too, it's learning. I haven't done this experiment before. I realize momentum. Do you notice it came much further?
Mm-hmm.
But it still seems to be getting stuck, because once you hit a deep enough pothole, there is no escaping it, isn't it? Let's look at it from the side. See, it came way, way further than before, but it got stuck here. What is it that we can play with? Hey, we forgot. We did not look at the learning rate.
Yeah.
You know, well, let's make it, even though it has momentum, let's give it a high learning rate, right? Let's give it a big learning rate. Maybe I'll do ridiculously high learning rate, and I'll start at the same point, right? Let's go here. That doesn't seem to be helping. What is happening, guys? Let's look at it. What is happening? It's dancing all over. It's hopping, bouncing, and going everywhere except the minima. It even touches the minima and runs away from it. Do you see this, guys?
Yeah.
So this is the problem when your learning rate is too high, right? So now let's try the same problem, and I want to take the same spot. Where did we start from? Somewhere here, right? This point. Now we are going to,
Asif,
yeah, go ahead.
in case the learning rate stays this high, is there going to be any point in which, or does it remember all the points that it has traversed and maybe
No.
select the local minimum in the end?
No, it doesn't. That's what you would do. What you do is you basically have to snapshot the model all along the way. That is a terribly inefficient way of doing it. So there's a better way. Suppose I make the learning rate more reasonable. See, I'm decreasing the learning rate in the lower right. Do you see me do that?
Mhm.
Let's take a number that is more reasonable, 3.3. I'll start at the same point. We started here or there, I forgot which side, left or right? I started from here, right? Okay, I'll start.
Yeah.
Right. Ah, what happened? This
Slower
is Goldilocks,
rate help.
right? Yeah, we came down with momentum. We didn't get trapped in local minimas, right? Little potholes along the way. And look at this. We never got trapped. We had enough momentum and our learning rate was good. We are still bouncing around the minima. Look at this. If you look at the coloration, it is still not sure which point is the minima. It's bouncing around, right? So go ahead.
I think for a, like for a general problem, I don't know, maybe you covered that point. For a general problem where we don't visualize this kind of a loss function, right? Starting with a big learning rate and gradually reducing it in our journey and the momentum helps. Is that a general solution?
That's sort of what we are coming to. So from this, we are asking the intuition. So what are we learning? If you look at it, when in the beginning part of the journey, see, suppose you start from here. Let me take another point. I'll start from here. Do you notice that you got trapped in this place? Right? High up, you got trapped. So at this moment, you would really hope in the beginning of your journey, you know that you'll start at some very inefficient place. At that moment, good momentum, good learning rate, they all help you, right? High learning rate helps you. It gets you over the pothole. The trouble is, as you progress in the learning, after a little while, a big learning rate fights you. It doesn't let you sit anywhere near the minima. It makes you bounce around. So the intuition that you take away from is, let's do one thing. Let's have an adaptive learning rate. In the early epochs, let's have a high learning rate. But once we come close to the solution, because high learning rates will help us get over all the false minimas and hopefully get us closer to the global minima, right? But once we come there, then let us slow down. Let's not take big steps. If only we could have an adaptive learning rate, that would be to our great advantage. Would you agree? Does this make sense, guys? Huh? So that is one lesson, that the learning rate cannot be a constant throughout the epochs. Let us change the learning rate at each epoch. So, and how we change that, it is called the learning rate schedule. The formal term is learning rate schedule. But all of these schedules start with one principle. High in the beginning, progressively smaller as you come towards the end of your epochs. Because the hope is towards the end of your epochs, you're very close to the solution, right? So to be able to modulate the learning rate, to have it adaptive based on the epoch you are, and at each epoch, or progressively bring it down. You are using a adaptive, or you're using a learning rate schedule. That's a formal term used. PyTorch also, the API will call it a learning rate schedule. Now, there are quite a few methods to do learning rate schedule. And I will walk you through one by one, each one of them. Before I do it, I want to mention two problems that happen in the world of gradient descent. One is the problem of exploding gradients. If your gradient is too big, it's tending towards infinity. However low a learning rate you take, you're still taking a giant step. Does that make sense? Because the step size is learning rate times the gradient. Isn't it? Are we making sense, guys?
Is it because the valley is too deep?
At some places, you notice that it is, look at this. Look at this surface, this part. Doesn't it feel almost like climbing Mount Everest? Where my mouse is, right? So there are regions that you can't avoid where the learning rates are, where not the learning, sorry, the gradient size is very high, positive or negative, it's very high. In this, you don't see very strong positive. There are strong positive gradients. See, you see on this side, if you're bouncing off and going up, right? There are strong positive and negative gradients, but it's just mountainous. In this high mountain range, gradients can be very, very steep. Practically, vertical fall means the gradient is close to infinity.
Infinite, yeah.
So what happens is when your gradient is close to infinity, even a modest learning rate will make you take giant steps. Or in situations when you're doing the back propagation and so forth, your gradient may actually become infinity. It becomes, see, computers don't have infinity, they have a max number. And those max numbers are intractable. Yeah. The learning becomes haphazard, like it becomes problematic. So that is one problem. The other problem that you have is that of vanishing gradients, the opposite problem. Vanishing gradients is when the gradient tends to zero. And that too happens. Look at this. Do you see a lot of places where the gradients is close to zero? Yeah. All these little valleys, local minimas and so forth. Right. So you want the gradient to vanish at the true minima, not just about everywhere. Not, not get trapped into all sorts of places so that you stop making progress. Now, vanishing gradient is a problem. In back propagation, in neural networks, it's a nuisance because they are trying to propagate the gradient at any one stage. If the gradient is already close to zero, the layers behind it will not learn anything because zero doesn't transmit any further signal back propagate any further signal. Go ahead.
That's where all the local minima are by definition, or?
In the loss landscape, yes, but it becomes very practically, right? Imagine that one particular node, and there for its parameters, the gradient has vanished. Right. So it has stopped learning. It can't learn. So that neuron practically becomes a dead neuron. And it starts affecting the neurons in the prior layers because this is not doing anything. It's just a dead neuron sitting there, right? So these are practical realities. And so there is a whole bit of theory why, and let us go through that now carefully, now that we have done this, but keep this intuition in your mind, guys. Observe the fact that neural networks are a highly, highly non-convex structures. The loss landscapes are very, anything but like my beautiful convex bowl, right? Is the antithesis of that. So with that intuition there, and I'm deliberately going slow today, so we get this right. Let's come back to it. Now, what can happen? Let's go back to the basics and see what can happen. And there are quite a few learning. So see, let's go back to this equation. Our equation was, original equation. So I will now, see, I wrote the equation as W next is equal to W minus alpha, gradient of the loss, this. But so that you can review from this new textbook, they use a new note, they use a slightly different notation. They call it theta, right? And instead of calling theta tilde, they say theta t plus 1, that is in the next iteration, is equal to whatever value of theta is in the previous iteration minus, and the alpha goes, they call it eta. This is the word for that is eta. Eta. It's a Greek letter, eta. Is the learning, it is still the learning rate, and this is still the loss function, but loss function is a function of theta, right? So loss function is still a function of theta, right, instead of W. So it is just W gets replaced by theta, guys, huh? And alpha gets replaced by, in this book's notation, alpha gets replaced by eta, right? So we will follow this convention, nothing new. So just for one moment, absorb that I have done nothing new. Just this book follows a slightly different convention, and you'll have to get used to the conventions of different books and different things. So long as you can recognize the pattern, you can always map back to your language. So take a moment to absorb this, because I want, the reason I'm using the notation of this book is so that you can go back and review it. And the next book you pick up, it will use its own notation, right? So you'll have to become familiar. It's like, you know, you're reading your colleague's code. He doesn't follow your naming convention. So you have to get used to his coding style. So it's the same thing. So far, so good, guys?
Yes.
So now what it says is, every time you take a step, so this is step T, at step T. Now, what is a step? Remember, our two main loops were for epoch I in, let's say, epochs. Let's say epochs is equal to, pick a number, let's say 100, right? Example, epoch. For each epoch, for step, like for batch, mini batch, J in data set, do the 4 crucial steps, the inner loop. The inner loop, I'll just put it here. What is that? Prediction, y hat is basically your, whatever the function is, function of the, whatever current values of theta are and x, like the input. Input goes in, given whatever parameters you have, if this is the same as whatever weights you have, you realize that the output is a function of the input and the weights. Yeah, that is it. That's number one step. Now, what do? The next is loss. Loss is some loss function of y hat y, the actual labels, right? This is the prediction. This is the actual. What do we do next? What is the third step?
Compute the gradient.
Gradients. And what is the final step? Update. And in the language of this new thing, this is equal to theta t minus eta gradient. The step of learning. Now, let's index the step of learning with t. The t plus 1 value is the tth value minus eta this. So I hope by now, this should be fairly familiar. This is machine learning. And especially in the neural network sense, it is true for all machine learning, but here we are talking neural networks. This is how you train. So far, so good, guys? Mm-hmm. Now comes this question. If eta, the learning rate, is not going to be constant, we just decided that in the beginning, the learning rate should be high, then progressively it should decrease, right? So what we really want, let me just write it. What from intuition gathered where? By looking at that loss landscape, we learned we want something like this. Suppose this is t, the step 1, 2, 3, whatever t is this, and this is the eta for that given value of t. Okay. What we want is that the learning rate should start high, and at the end of the epochs, it should end low, right? So now I'll put the constraints. What would be a good way to play with the learning rate? Do you think we should do like this?
No.
Well, you don't know. Peculiarly,
Yeah.
right? It turns out that your first reaction is no, there shouldn't be it. You may say, well, this is a better one, right? But maybe this is certainly bad. Like this, you don't want to do, right? Who knows? You don't want to increase and decrease it or something like that. What is a good learning rate? Or should we go like this? Right. So I will mention, right? Or the one thing is, if you don't play with the learning rate at all, then what happens? It remains the original thing that we have been doing so far, which we in hindsight know is not a very good idea. The initial learning rate and the final learning rate remains the same, right? But we realize that gets us into trouble. So now what is a good learning rate? People have learned from experience. Now, some of them look reasonable, like the yellow one looks reasonable. The green one looks reasonable. They have names actually. This is the exponential decay. This is obviously linear, but linear is rare. I mean, I don't know. You can play around with linear. You can see whether it works. There is actually another learning rate, which is very fascinating. It doesn't come down, but it comes down in steps, but I need a color for that. Maybe I've exhausted all color. Maybe I'll use white. Yeah, so there is a learning rate that says like this. It just comes down a few times. You see that? It takes a stepwise journey down, but it never actually goes to zero, right? So this is the stepwise, and there's a formal name for it. I'll look and tell you. But one that surprises you is that something that oscillates like this, you know, your first reaction to the pink one would be that can't be right, isn't it?
Yeah.
This one can't be right. But counterintuitively, there is quite a bit of theory that actually these learning rates are pretty good, right? A learning rate like this, and there's a whole broad family of them, and they're like, so the word that is used comes from intuition from thermodynamics and material science. It is called annealing. There's a process called annealing. What is annealing of metal? See, if you have a metal that is very brittle and hard, and you want to make it soft and ductile, it's stretchable and nice. But the reason it is hard, this is a bit of physics, is because when you cool a metal, like, you know, you purify a metal and you cool it, it has something, it doesn't have a perfect crystalline shape, right? So what will happen is it will have this defect. There'll be a microcrystal pointing this way, another microcrystal like this, another like this. So it won't form a nice joint lattice structure. So there'll be little sublattices, and the boundaries at which they meet are called the defects. And those defects contain a lot of energy. So what has happened is that this entire metal, it has cooled to a equilibrium, I mean, a stable state, which is actually higher than the minima. The real minima state would be a perfect lattice, right? One continuous lattice, no tension, and there's none of these defects present in them. So what people do is that they will reheat the metal and then use some form of cooling, either slowly cool it down, or they will quench it for copper, like put it in cold water and something like that. But all the time, what they're trying to do is they're trying to reduce the number of defects, crystal defects, right? And when you remove the crystalline lattice defects, it becomes more and more a more perfect lattice structure, relatively speaking. And the more closer it comes to be defect-free or more geometrical lattice structure, the more it has ductility and the good properties that the metal is supposed to have, right? So, and those energy states are low energy states. They're minimas in the energy level. Whereas if you just take a piece of metal which is hard and brittle, but shouldn't be, it has just stopped or cooled off to a high energy state. Now, does that have a parallel to what we are doing? We also have the same situation. We fear getting stuck in local minimas. So what do we need to do? We need to reheat essentially the thing so that it bounces off and the atoms start diffusing again, and then gradually they get a chance to recrystallize, and hopefully at a lower energy state with less defects. The same analogy is here. Now, suppose you get stuck in a local minima, right? Lots of local minima. You're here. What do you need to do? In a local minima, you have a certain learning rate. How do you escape out of it? Reheating is the same as increasing the learning rate. Are we together? Right? You can, I mean, it will have past momentum, but suppose it stopped here. What you want to do is by reheating means you're exciting it. You're forcing it to just bounce around a little bit and search for a better minima. When it does that, it will bounce to this, maybe get stuck here, then bounce off it, and finally get to the minima. But what will happen when it bounces off here and there? Right? It will
Escape.
off there. It will stick there. It is not going to jump back to one of the suboptimal minimas. So this is the process of annealing. And there's a vast amount. This is simulated annealing because we are not doing it with metal. We are doing it with a loss landscape. Our learning rate and progression, we are trying to anneal the whole thing. People use the word cosine annealing. And there are many variants of it, many cousins and many friends of it. Right? So this topic playing around, when we say that we are going to replace theta t plus 1 is equal to theta t minus not the fixed learning rate, but a learning rate, people use the L, it's unfortunately the symbol L is used, which is a function of the starting learning rate and which step are you at? How many steps have you taken so far? Right. So the idea is that at each step, you'll keep changing your learning rate. For example, here, the green line, it is at each step, it is decaying the learning rate. Right? Yellow one is also decaying the learning rate. Right? It is some function times the gradient of the loss function. Right? It is this. So this is called learning. This function is called learning rate schedule. Learning rate schedule. Right? Very important thing. It's one of the things that people often miss, and you will often find that books, most of the books, they either gloss over it or they don't talk about it so much, at least the older books. But the reason I'm recommending you guys get this is this book very nicely explains the learning and the various learning rate schedules. Yeah. PyTorch has excellent support for it. All the good standard learning rate schedule functions are built in. The green one is built in, the white one is built in, that weird oscillating one, the cosine annealing is also built in. And there is one more, something called plateau learning. I'll tell you about it. That also is built in. And there are many more that are built in. So it's lovely. You know, the beauty of PyTorch is when you scratch the surface and go deeper and you see all these treasures, then you begin to value it more, right? So obviously, TensorFlow also has it. So these two are the sort of competitor ones. They have a wealth of treasure built into them. So now let's take examples of learning rate schedules. We have, it's 9:06. I will go over them relatively quickly and you will see. So let's take the green one. The green one in this picture, when you look at it, how is it doing? It's exponentially decreasing, isn't it? What could be a function for an exponentially decreasing learning rate? do is,
If over minus 6.
go ahead. Somebody said something, please go ahead. No, okay. So
E to the power minus t.
very, very close to it. What you do is you say that the learning, so let's take the, let me use green color so it will match what we are saying. Exponential decay. See, if you're a physicist or mathematical physicist, this, if you ask them, I want something to go down, their basic instinct, I don't know, for whatever reason we are trained not to think linear. We'll always think exponential decay, right? Because most of the things in our world, in physical world, they tend to decay exponentially, right? So you could do it in many ways. It is basically the learning rate at a given point, at a given step t, is the original learning rate, which you want multiplied by a decay factor. Now, one of you said you could do e to the minus something or the other decay factor, right? All of those are valid, but this also works. You take a certain gamma, which is the decay factor, and you exponentiate it to the power t. By the way, a gamma to the power t, you realize, can be written also using e. How can we do that? Let's say y is equal to this, log y would be t log gamma. And so y would be e to the power t log gamma, isn't it? So your intuition is not far off, right? And if gamma is between the range 0 to 1, is smaller than 1, right? If gamma is 0, obviously bigger than 0, what happens? If you take log of a number between 0 and 1, what is it? It's negative, and so e to the minus negative something step. So it's a decay function, but this works. So let's take this as an example. Let's say that your gamma is 0.1. At step t is equal to 1, what will be your learning rate?
Was it positive t or negative t?
T is a step, which step you are on. So start
Okay.
step 0. So L and not 0, the first time,
1.
it will be 0.1 to the power 0 is equal to just eta naught, because this will resolve to 1. Anything to the power 0 is 1, isn't it? So this is your initial, remains your initial learning rate. Let us say not 1 at the first time. This will be naught times gamma to the power 1, which is basically 0.1 times the initial learning rate. So it means that at each step, you took the learning rate down by 0.1, isn't it? Then L naught 2 is what? It will be, you can convince yourself that this is 0.1 squared times eta naught, right? So likewise continue L5 to, what is this? Eta naught 5, basically step 5. 0.1 to the power 5. Now, how do these numbers behave? 0.1, 0.01, 0.00001. You see how quickly it decays? Learning rate decays, right?
Yeah.
That is it. So it's a decaying learning rate. Now, typically, you don't take gamma this small, right? You take gamma a little bit. This is too big. You take gamma a little bit, like, I mean, it depends how you do it. 0.01, point, whatever it is, you can decide. The best way to do that is to decide what you want your final learning. Suppose you run for 100 epochs. Let's say that the number. So guys, this is very fascinating. So I hope you're paying attention. Number of epochs you have in mind is T. Say, I don't know, 100. Right? Then you start, let and not the initial learning rate be 0.1. Let's say that your final learning rate, where you want to, because you don't want the learning rate to be too small. What happens if your learning rate is way too small, like 10 to the minus 10? You're in trouble, because close to the optimal solution, gradient will also vanish and your learning rate will also vanish. So the system will stop learning. So you will actually want to take a reasonable learning rate. Let us say that the learning rate that you take is, I'll say 10 to the minus 4, right? And this is equal to 10 to the minus 1, right? So now the question is, you decide to take t steps. What do you want? According to this formula, your learning rate and eta min is equal to the learning rate gamma, whatever the gamma learning rate is, to the power t, t being, let's say 100 times eta naught. So you have a min max in mind, starting learning rate and final learning rate and the number of epochs. So you realize that from this relationship, you can calculate gamma, isn't it? What is gamma? Gamma is essentially, it is equal to min over eta naught, basically 1 over t, or another common sense way people think of it is a tth square root, or it is the same as eta min, eta naught to the power 1 by t. You agree with that, right? So you can now feed in the numbers and figure out what is a good eta. And that is the way people do. They have a number of epochs that they want to run in mind. They pick an initial learning rate, they pick a final learning rate, and so they can find a good gamma, and it works, right? It works quite well. So far, so good, guys. It's just that, see, guys, these are just mechanical details. There's nothing magical about it. So long as you realize that we want to do exponential decay, this is the way to enforce exponential decay. Good so far, guys?
Mhm.
Yeah, okay. So now that is that. And you say, well, does it actually make a difference? And why will it make a difference? It makes a difference because, you know, the one analogy that people give, and this book also gives, and you'll often hear in the industry, it's more or less a right analogy. It says that, see, when a train is coming, like, you know, you all take the BART. When BART is coming to a station, what happens? It slows down. Otherwise, it will overshoot the station. You don't come towards the station at full speed, the same speed at which it is crossing vast distances. A train, when it is going through basically middle of nowhere, it is at full speed, right? Because it should be at full speed, right? But once it is out of the wilderness and it is coming towards a station, what should it do? It should lose speed. Does the intuition make sense? It should be losing speed. So the losing of speed is slowing down the learning rate. You're coming towards the target slower, you're approaching it so that you don't overshoot it. Is the intuition making sense, guys?
Yes.
Right. So now let's take the next one, the step one. By the way, I leave the linear one as an exercise for you. Think what is the equation that you would write to have a linear decay of learning rate? Whether it's a good thing or a bad thing is separate, but just as an exercise, try to work it out. It's very easy, you'll work it out, but do it. Now, what about the step one, the one that takes 2-3 steps? Experience shows that taking 2-3 steps works quite well, actually. Sometimes all you need to do is not exponentially decay the learning rate. Sometimes some people say, well, too much hard work. Let us just, for first 50 steps, let's keep one learning rate. Next 50 steps, keep another learning rate. And the next 50 steps, keep another learning rate, right? So learning rate you change after 50 epochs, assuming that you are you're running it for 150 epochs. Are we together? Right. When you do that, guys, just give me a moment. There seems to be a version coming. Please pause it. Left my one of my work team members in my team has just had a baby girl. He's very excited and he's giving the good news. It's always such a great experience to be a father. So the next learning rate we'll take is this, a step drop adjustment. Like just make a few steps, don't get too fancy. So what color did I use for steps? White. So well, let's write this notes in white. Step adjustment learning rate. Right? So now there's a bit of, there's a one problem though with the exponential decay. What happens is when you decay so slowly, it's a little bit erratic for reasons that we won't immediately go into, but I invite you to read in the book. Basically what happens is that you're losing momentum and you are like, you don't know how well you're converging. But anyway, for many reasons, we'll talk about it in the second pass when we go over this in greater detail. So I will say step drop, and I'm literally using the conventions of this book, adjustment. Its defining quality is it gives you better smoothing, smoothing. What is smoothing? Which smoothing? When you plot the accuracy, for example, let's say that accuracy is a measure, and as the learning progresses, as S progresses, what happens is your accuracy could be going up, it could be oscillating, or it could be smooth, right? Which one it is depends upon what kind of a learning rate scheduling you do, amongst other factors. Gradient, we haven't touched the gradient function itself. We'll touch that. Actually, I'm surprised we already took so long, so we'll keep it for the next time. But okay, what is this smooth? It basically empirical evidence is it's a little bit smoother way there. Now, this is very simple. If you want to just take a few simple steps, you need to say after how many epochs will you take the step? Let's say that you want to take step after every 50 epochs. Then how would you write? So your S is 50, and you write your equation like this here. Eta t is eta 0, the initial learning rate, right? Which is basically this is your L, eta naught t is equal to this. These are just notations, and what you do is you still have your gamma, but gamma, the exponentiation of the gamma is not t, but it is t divided by S. And are you guys familiar with the floor symbol? Floor is given a floating point number, the integer, so suppose it is 3.14, right? Forget the fraction, what remains? 3. That is your floor, right? You round it off, round down to the integer. Right? When you round down to the integer, it is called floor. So it's one of the things in your first like computer science 101 class you must have been taught, but we tend to forget, is the floor symbol. Now let's see what happens. Suppose your S is 50. Then let's take T value 23. What will happen? What is gamma 23 divided by 50 floor? Can somebody tell me what is this value?
0.
0. Yes, this would be 0. So anything up to 49 will be 0. 0 to 49 will give you, the floor will give you 0. 50 to 99 will give you what? 50 divided by 50 is 1, right? And 99 divided by 50 is still 1 point, some number less than 2, isn't it? So therefore the floor is still 1. Then 100 to 149, floor is 2, right? So now what happens? Look here. there are only three values of the flow of this eta of the eta that you will get. Gamma. What is gamma to the 0?
1.
And gamma to the 2. So this is 1. This is, well, gamma, and this is gamma square, right? So let's say your gamma is at 0. Pick your gamma. Let's say your 0. Typically, gamma in these situations, gamma that people select is in the range of 0.1 to 0.5. Why? Because let's say that you make it 0.1. What is 0.1 square? So the first step will be 1/10, and the second step will be 100th. Isn't it? The learning rate, in the first step, it falls down to 1/10. In the next step, it will fall down to 100th. Does that make sense, guys? Right?
Yes.
That's it. And then you can work it out for 0.5. First step, it will be half. Second step, it will be quarter, right? So the bigger the number, the slower the damping of the learning rate. So this is called the step drop adjustment. And then comes the crazy one, the cosine annealing, which actually is, you can imagine that if you bounce around with the learning rate, it's not going to be terribly stable. But surprisingly, it gives you very good results. And there is a whole body of research into it. And the reason it works is quite interesting. If you keep annealing out of local minimas, why would you want to do that? A whole bit of mathematical argument and research and experimentation has shown that local minima exist close to other minimas which are better than this local minima. Right? So there is a whole cascading set of minimas that you can journey through. It is not that the local minima is isolated and then you'll climb a long hill and then go back to the next minima. It isn't like that. And you can see it in this visualization, in this real. That's why I like that visualization. Where is it gone? All right, let's revisit this. Look at the local minimas. Do you see these local minimas? Do you see how they are close to each other? That next to this local minima is another minima that falls here. Next to this minima is this minima, bigger minima, right? All these minimas, they are not, I mean, I don't know, if you look at it this angle, you see that these minimas are all pretty close to each other, isn't it? Right? So it means that if you boil yourself out in using the physics intuition, if you really boil yourself out of a local minima, you are well on your way to the next minima, isn't it? Right? And that is the intuition behind the next one, which is the cosine annealing. Remember, it's a very physics intuition here. So its quality is great accuracy. It actually ends up leading to models that have very good accuracy, but rather unstable, but can be rather unstable, right? You have to play around with it. So what you do is you want to make sure that, say, suppose, how does a cosine wave go? A cosine wave, if you remember your basic trigonometry, at 0, what is cosine of 0? 1.
1.
What is cosine of pi by 2?
0.
1,
What is
0.
cosine of minus pi? Sorry, pi. Pi is -1. Right? It is -1 here. And then it again starts climbing back up. This is 3 pi by 2. And finally, if you go to 2 pi, this 2 pi, it goes back to, so this is one entire wave, like one wavelength, right? So this is 2 pi. Are we together? Now, I won't belabor you with those basic equations of motion, wave motion, and so forth. Suffice is to say that if you remember a formula like this, y is equal to cosine 2 pi ft, you are actually doing very well. This is t, this is y. F is the, does anybody remember what the word F might be connotating? Frequency.
Frequency.
How many times it beats in unit time, right? So we will. So now the problem is, how do we use this? Well, we don't want negative learning rate. That doesn't make sense. That's silly. So what we do is we take a baseline. We take this amount, this range, -1 to 1, and we remap this range to this range, to eta naught. So the maximum is eta naught, and the minimum is whatever value we choose. So pick some minimum learning rate that you have in mind, right? And eta naught. Now, how do you map this to this? Oh gosh. It is basically a simple way to scale it. But what people do is the formula that we use is not that hard. First thing you do is you take eta naught minimum. This is the value you want to have. Then you look at the gap between these two, right? And you look at half the gap between these two, and you say eta naught minus eta min, right? Which is the range, R. Because that is the range. Now, what is the amplitude of this wave? Amplitude is half this maximum swing, isn't it? That is where the half comes from, amplitude. So this part becomes, and again, I am reminding you of things you may have forgotten. This is the amplitude of the cosine wave, right? And finally, of course, the cosine. Well, I have screwed myself because I have written it cosine. Let me just write this term properly in a lower line. And you will convince yourself that this works. This is what this is doing. T, right, is equal to eta min plus, because this is the minimum you want to start, half the amplitude being min, and the way I look at it is the amplitude of the wave times the cosine. Cosine will be what? And so 1 plus cosine. The 1 plus cosine guarantees you. See, if cosine goes to -1, if you add 1 to it, what is the range now? From
0.
1 to 0 to 2. And a half of that will be 0 to 1. Isn't it? So, which is what you're trying to do. You do 1 plus cosine, and the rest of it is obviously, by now, the intuition is trivial. You remember the pi that I brought in, 2 pi f. So I'll let you figure out in this what is the frequency. Now, T max is what is the number of epochs that you want to run for, right? So let's say your T max is 150 or whatever it is, do that. Right? So this equation looks very complicated, but if you are familiar with cosine wave, this is a straightforward equation, right? Think about it, play with it, review the book. And when you do that, and what I would like to do is show you some beautiful visualization that this has. The trouble is T max now becomes the hyperparameter of the model of this learning thing. Means you need to scratch your head and ask what is a good T max and play around with it. So one intuition that people do is they ask how many oscillations, how many times in the world of annealing, people ask how many times you want to reheat and cool the system, right? The physical intuition. How many times you want to re-increase the learning rate and bounce back? You pick a number that I want to reheat it or do the annealing 5 times, 10 times, or whatever it is, right? And let us say that you say, I want to do the annealing 2 times, right? Or whatever number of times. So what you do is, suppose you want S dips. S dips means S times you want to go up and come down. Then there is a formula. You say that your T max in this equation is T, the number of epochs, divided by 2s minus 1. So if you want 2 dips, 2 times 2 is 4 minus 1, 3. So total number of epochs divided by 3, plug it into this equation. And you can do this, by the way, you can derive it on your own if you understand what cosine is. These algebraic details don't matter. But the good thing is you need to end in a dip. Means you want to end your learning, like at your last epoch, you want this learning rate to be at its minima. Are we together? So you keep bouncing back from minima, maxima, minima, but you want to end in a low note, low learning rate, because presumably you are in the valley, right? You are in the bottom. You don't want to bounce back out with a learning rate. You want to sit there. You can say, okay, I'm done. So this is it. Now let me do one thing. Today, and there is one more, plateau learning rate. I don't know, we are running out of time. Let me first show you guys the visualizations because I don't want to miss that.
A little further down.
Oh, this one.
There we go.
Yeah.
Further
2s minus 1.
for 2 epochs.
Yeah, s being how many dips do you want? How many bounces do you want? Now, all of these things, let me visualize it. Let me bring the book and we'll visualize it. Time to look into the book. There is one more, it's called the plateau learning rate, which is very interesting. Let's do it next time. And then we have to still do the momentum-based methods, which we haven't done. This is the second half of the story. Guys, next week, I don't know how many days I'll be missing. I certainly won't be there on Monday, but the reading thing is, you guys must read these chapters. Kyle and Kate, they will create some lab on the scheduler. Kyle, I'll explain to you how to do that. Create some labs, walk people through it. At the same time, there is a homework. The California data set, housing data set, you need to, the homework for everybody is, and Kyle, work everyone through it. Just create a simple neural network, right? 3-4 layers, 2-3 layers. And as a regression problem, just using the regression neural networks we have. Apply the regression neural net to the California data set and see how good a model you can build use on the California data set. Yeah. California data set is there are certain features about a home and you have to predict the price of a home. Right?
Okay.
California housing data set. You remember that California housing data set, right? From the,
Yes.
all of you must be remembering it from ML-100, 200. So let us bring that back. In this week, this is a project for all of you guys. Please try it. All the code is there. The regression code is there. Neural network is there. Use that and apply it to the California data set and try to do it on your own, guys. Finish it. And then, of course, take the help of teaching assistants, but do it. All right. So now that is your homework. And if I return before, no, I don't think I'll return on Tuesday itself, but just in case I find, I'm going there to Seattle to find housing for my daughter. But if I come back before that, then we may hold a Wednesday session, but don't be hopeful. It's quite likely that the whole of next week will be a washout, but Kyle and Kate, they will be with you and they'll be holding some sessions. So,
So we'll have the sessions, they'll just do help sessions.
there'll be help sessions, exactly. Right. Extra help sessions. And when I come back, I'll obviously continue from next week where we left off. So let me make sure that I got my equations right. Yeah, those all look right. See, what happens is, when you create a fully connected layer, right? If accuracy is your measure, then do you notice that, pay attention to this part. Look at this. What is it doing? Is it going, sorry, why is this not taking up? So this is not a very perfect tool, but is it smoothly in learning and improving the accuracy? Or is it sort of bouncing around it? At each step, the accuracy goes up, goes down, goes up, goes down. What is happening? it's a bit stochastic. It's sort of bouncing around, isn't it? The learning accuracy for each epoch, the test accuracy, what matters is on the test data, or the evaluation data. It's not doing well. It's sort of bouncing around. That is the problem that we are trying to solve. When you're learning, when you just use a simplistic fixed learning rate, fixed and no momentum and so forth, you end up with a situation like this. We want something like the red, which would be the ideal situation. Instead, what you see is this.
And that's the circumstance of what again?
It's just not using any of these things, using just a simple plain vanilla gradient descent.
Oh, okay,
Stochastic
stochastic
gradient descent.
gradient.
Yes. Now what happens is we will leave that.
It's still the one.
Yeah. See, what happens is that now let's look at this. And I think I can zoom into the top one for the time being.
Until the bottom.
No, I'll remove it.
Thank you.
Yeah. So suppose your learning rate is high. Look at the picture on the top. What happens? You're taking giant steps. So do you notice that your trajectory, what is your trajectory? Are you reaching the minima? The minima is in the center, the deep green place. Are you reaching that, or are you happily bouncing around it with energy? Do you notice that you're bouncing around it? Are we together, guys?
Mhm.
So if you, on the other hand, if you now, and let me remove this, look at this. Look at the picture here. And if you look at this a bit more carefully, look at this part. Do you notice that the steps are becoming smaller?
Mhm.
Now the size of the step also depends on the gradient. If the gradient is high, then you will be forced to take a bigger step. But at least the learning rate, as it progressively decreases, do you notice that it zones into the solution? Right? It goes and hits the solution. It doesn't take a straight path to the solution, but still, it at least reaches the solution, unlike the figure above. Right? So that is the value of a decaying learning rate. Now, we talked about 3 different learning rate schedules. Let's look at those. So one is the flat one, like you don't change the learning rate at all. Then there is the blue one is the exponentially decaying learning rate. And the green one is the stepwise, isn't it? The stepwise. So the red is no learning rate schedule, just flat out learning rate. This is how they look by epochs. Remember, learning rates you change on an epoch basis. Then comes now let us bring this crazy cosine one also. Now that looks pretty crazy to anyone till you think about the whole theory and you realize that the loss landscape is filled with local minimas. And then if you have a background in material science and physics, you say, aha, 100 years ago, we figured out how to solve this. We need to do annealing. Right? So a cosine annealing is quite popular and its variants are quite popular. They do the job. What you do is you essentially reheat it. Reheat the learning process. You just accelerate it a bit, then again cool down, again accelerate. You do all that. So here your learning rate is bouncing back and forth. Are we together, guys? Do you see? Right. Now, what is the consequence of doing this? Let's look at this. And I have highlighted a sentence. Now, why is it that this whole bouncing back is good? So we have learned, and by the way, the hard math is obviously a lot to do with simulated annealing and the theory behind it, but we won't go there. So through experimentation and hard math, we aren't going to look at, there is a common phenomenon that suboptimal local minima exist on the way towards the better minima. We saw that in the visualization, guys. On the way to the better minima, you come across a lot of suboptimal minimas, right? So that is the point visually that you can see here so clearly. The book is saying. So if we shrink and then later increase the learning rate, and in my language, reheat the system, you can give our model a chance to escape the current local minima and find a new alternate minima. So look here. Look at the picture above, guys. Huh? This picture. And let me keep on. Do you notice that you start from here and you came here? If your learning rate remained fixed, or any one of the other things, what will happen to you in this local minima? You will get stuck. Do you see that? But this local minima is actually on the way to the global minima. So if somehow you could reheat your way out of it and bounce out of it, you would be well on your way to the better minima, which is in the lower half of the picture. Do you see this? When you do the cosine annealing or any annealing technique, the point of annealing is you're always suspicious. Are you that you have reached the maxima, the best minima? You're always suspicious that you're trapped in a local minimum. So what you do is you keep reheating and coming out. Bounce out a couple of times. If you're truly at the best minima, you'll bounce out. You won't be able to easily bounce out. You'll stop there. Right? That's the point. So here we go. You notice that it gets a little bit into the local minima. It isn't that it escapes the trap altogether, but it reheats its way out of it and bounces on its way to the global minima, right? Or a better minima from there. And it again points to the fact that we were seeing visually that there are many local minimas on the path to better minimas. Right? So that is worth knowing about. We won't go into the code aspects because we are going to eventually do it in the lab. There is one more strategy which we'll talk about later next time. And I want to show the experimental results. Yeah, this part I wanted to show. Look at this. See, there is a rule in machine learning which is called no free lunch theorem. Means you never know what algorithm or which approach will work best. Data rules. So any kind of a graph that you draw is very dependent on what data set you used. But generally, the plain SGD sort of oscillates a lot. If you look at the cosine, do you notice that the cosine, I don't know if the colors are very clear here, the cosine, I'll just point to this cosine. Do you see? This is the cosine one. It is doing quite well. It also has its oscillations, but it is doing quite well. But here, the green one seems to be doing pretty stably. You see, the green one is not that bad. It's pretty close to the best one. Is doing. So for this situation, it is. And the one that's doing the worst is, it so happens, is the exponential decay one in this situation. Right. And then the cosine one. Yeah, the cosine one does the best. And where's the plateau one? The plateau is the and plateau is not far behind. It is the purple line which you can't make out on the screen, but it is doing quite well. It also, so the top three winners are the cosine, the stepwise, and the plateau. The plateau one I'll explain to you next time. We seem to be running out of time and I would like to take questions now. So guys, is it fun? Did you feel you learned something fun today?
Yes.
Yes, sir.
Yeah. See, a lot of it has to do, if you want to be good in this field, get your intuition from the math, because libraries will come and go. Today's TensorFlow, PyTorch, God knows what it will be tomorrow. But if your foundations are strong, you'll do very well. Because these things will remain. Right? So I'm thinking about these things will remain. So we have covered only half of the part. Remember, we started the session by saying we are going to rethink the learning, which becomes a learning rate schedule. And we will even rethink how we update what we do with the gradient. So the gradient will become a different function. I don't know, did I say that or not yet? Yeah, here I stopped and said the eta, the learning rate schedule. But now the other part of the magic, the gradient, it turns out that leaving the gradient to be just be the gradient isn't good enough. We need to bring momentum in for obvious reasons. We went through the intuition, but all that. So yeah, I covered both. But the momentum intuition, we will now bring it down to details in the next session. Right? And pretty much now we are coming to the end of the fundamental theory. I would like to finish all the fundamental theory in the next session so that we start going to the neural architectures. We will do, after this theory, you'll find the architectures pretty straightforward. The convolutional neural nets, the recurring neural nets, and then the one architecture, the two things that I'll really focus on in this course, time permitting. One is the attention models and transformers. Today, they are ruling the AI world. And the next thing that we'll do is the graph neural networks. I'll introduce you to that in this course. So, all right, guys, any questions?
Asif, quick question.
Yeah.
I don't see the previous classes YouTube recording. It's still a Zoom, cleaned up YouTube recording.
No, you go to the other, see, you are logged into the 2020 course, no?
No, Asif,
2020 course.
so it will be, no, this session's videos, I've sent it to Joel. So he was busy for a week, and that's why he will be sending it this week to me. I'll upload it and post it on Slack.
Was that your question, Praveen? But the videos of 2020 are available. You have access to them.
Yes. Yeah.
You remember, Praveen, that we didn't cover this last time.
Yes. Yeah. This was new. Yeah. No.
Yeah. So that's. Anything else, guys? Any new thing? Any questions?
What will be happening on the weekend? Anything, or will you be traveling?
Oh, I'm not. I'm flying out day after tomorrow.
Okay.
Friday, I'll be gone.
Okay, so we'll have like help sessions Monday and Wednesday evening. with,
That
like,
is
the
it.
entire-
That's right. And Friday, I mean, this Sunday, there will be no paper reading.
Okay.
Any questions, guys? All right, guys, then I apologize that we have to take a 1 week break, but I'm actually taking a break after a long, long time. I think this is my first break in this year. I'll be back, then we'll continue.